Hi, I'm teaching civil chemistry under the AQS specification. I'm on the Inorganic module and today I'm teaching periodicity. So the modern periodic table arranges elements in order of increasing atomic number. This arrangement reveals patterns in the properties of elements, which allows chemists to make predictions about their behaviour. The periodic table is organised into periods and columns. So elements in the same period have the same number of electron shells, and as you move down the period, the number of electron shells increases. And elements in the same group have similar electron configurations in their outer shell, and as a result, they exhibit similar physical and chemical properties. So the periodic table can be further divided into 4 blocks based on the type of subshell being filled in the outermost electron shell. On the left, we have the S block. In the transition metals, we have the D block. On most of the non-metals, we have the P block. And at the bottom, we have the F block. And you see helium, which is 1s, being above the P block. And that is because we know it has a full outer shell with 2 electrons because it's on the first outer shell, which means it can only be filled by 2 electrons. And because it has a full outer shell, it acts more like a noble gas, which means it's unreactive. And that's why it's put there, even though it has a 1s2 configuration. Okay, so now moving on to the trends and the properties of period 3 elements. So the type of bonds and the strength of bonds between atoms affects the melting and boiling point of elements across period 3. So here you see a graph and it has the different elements across period 3 and it shows the graph of their melting point. So you see the giant structures, silicon, which is at the very top, and then the simple molecules, and I'm going to explain each of them. So for the metals sodium, magnesium and aluminium, melting and boiling points increase due to the increasing strength of metallic bonding. And that increases because the ions have a larger positive charge as you get across the period. The ions will have a smaller ionic radius and there will be more delocalized electrons. So these factors all result in stronger electrostatic attractions between metal cations and delocalized electrons, which require increasing amounts of energy to overcome. And now we move on to silicon, which has the highest melting point. And it's because it has a covalent lattice structure where each atom is bonded to 4 neighbouring atoms in a tetrahedral arrangement. And this forms very strong bonds, which links all the atoms together in a 3D lattice. And a huge amount of energy is required to break these covalent bonds. And that is why it has such a high melting and boiling point. And now we move on to phosphorus, sulfur and chlorine. And they have simple molecular structures with only weak induced dipole-dipole forces, or Van der Waals forces, or London dispersion forces, depends what you call them, existing between these molecules. And these intermolecular forces are really easy to overcome, which means they have a low melting and boiling point. Sulfur has the highest melting and boiling point among the 3 because its molecular structures contain more electrons, and the large molecules allow stronger Van der Waals forces to form between the molecules. And chlorine has the lowest melting and boiling point among the 3 because its molecules contain the fewest electrons, and that results in the weakest molecular force. Now we move on to argon, which has the lowest melting and boiling point in the period, and that's because its atoms do not form any bonds, and it's only very weak induced dipole-dipole And now we move on to argon, which has the lowest melting and boiling point. Its atoms do not form any bonds and only weak. And now we move on to argon, which has the lowest melting and boiling point because its atoms do not form any bonds and only weak induced dipole-dipole forces attract them. So minimal energy is needed to overcome these negligible. Okay, so now we move on to argon, which has the lowest melting boiling point, and that's because its atoms do not form any bonds and only very weak induced dipole-dipole forces attract them. So minimal energy is needed to overcome these forces between the atoms, and therefore it has the lowest melting boiling point. And the atomic radius decreases across period 3, and this happens because as protons radiate across a period, the nuclear charge increases. This results in stronger electrostatic attraction between the nucleus and the outer electrons, which draws in the outer electrons closer to the nucleus. And with increasing nuclear charge and minimal change in shielding, the stronger electrostatic attraction causes the atomic radius to decrease across the period. So that means that because the nucleus becomes more positive, it pulls the negative electrons on the outside closer in. And because there's not very much change in shielding, which means the amount of shells between the nucleus and the outermost electron, it can pull it in quite easily. as it increases with positivity, basically, or nuclear charge in a more formal way. Okay, so now moving on to 8.3, which is ionization energies. So ionization is the process of removing one or more electrons from an atom or molecule, and this process requires an input of energy. So ionization is an endothermic process. And here you see the equation that represents the first ionization energy of magnesium. And the reason why I say first is because you can ionize multiple times, and I'll go on to that later. And when you write the equation, it always has to be positive ion plus an electron, because you can't take away an electron in an equation. So now moving on to the factors affecting ionization energy. So the ionization energy of an atom depends on how strongly its outermost electrons are attracted to the nucleus. There are three key factors that affect this. So the first is nuclear charge, and this means that atoms with more protons than their nucleus have a stronger positive charge, and this therefore creates stronger electrostatic attraction between the nucleus and the outer electrons. And now moving on to the... Okay, so now I'm going on to the factors affecting ionization energy. So the ionization energy of an atom depends on how strongly its outermost electrons are attracted to the nucleus. And there are three key factors that affect this electrostatic attraction. The first is nuclear charge, and this means that atoms with more protons in the nucleus have a stronger positive charge, and this creates stronger electrostatic attraction between the nucleus and the outer electrons. The next is atomic radius, and this means that electrostatic attraction drop off steeply with increasing distance, and electrons in smaller atoms are held closer to the nucleus, so the attraction is greater. So it's just the way that the nucleus pulls in the electrons, and as the distance gets greater, this becomes more difficult. So in smaller atoms, the nucleus can pull the electrons closer, so the attraction is greater. And the final one is electron shielding, and this means that inner electron shells shield the outermost electrons from the full attractive force of the nucleus, and this reduces the effective nuclear charge experienced by the outer electrons. So more electron shells provide more shielding. And this links in with the atomic radius, because greater shielding means the radius is greater. Because the nucleus cannot pull in the outermost electrons as much, so there's less attraction and less pull, which means the radius is greater, it's further away from the nucleus, and so it's easier to get rid of those electrons because they're not being gripped, they're not being held on as tightly. Okay, so now moving on to the trends in ionization energy. So on the left, you see it down the group 2. Okay, so now moving on to trends in first ionization energy. And on the left, you see a graph where it goes down the group 2 elements. And on the right, you see it across the period 3 elements. And so on the left, it's a decrease. And on the right, it's a general increase with 2 exceptions, and I'll explain those. So first I'm going to talk about how the ionization energy decreases down groups. And this happens because the nuclear charge increases down the groups as more protons are added, and this increases the attraction for electrons. The atomic radius increases down the group as more electron shells reduce nuclear attraction, and electron shielding increases down the group as more inner electron shells reduce the nuclear attraction. So the atomic radius and shielding effects down groups are greater than the nuclear charge effect, leading to an overall decrease in ionization energies as you move down the group. So despite the fact that nuclear charge is increasing, it's becoming more positive, and in theory should be able to pull in the negative electrons, the fact that the distance is greater and there's more things blocking the nucleus from the outer electrons, it can't pull in as much, and therefore it will lose the electrons easier, which is why the ionization energy decreases down groups. Because the atoms get larger, the elements get larger. And across periods, there is a general increase, which happens because, so the nuclear charge increases as more protons are added across periods. The atomic radius decreases across periods as there's extra electrons added to the same shell. And the electron shielding stays the same, or say similar across periods with no extra inner shells, because a period is just the same amount of shells with increasing electrons, but also increasing nuclear charge. And so the positive effect is more important than the negative one. So it pulls in the electrons with no blockage and can pull them in closer, and therefore is an increase across periods because there's more pulling, there's more attraction. between the negative and positive. And there are two exceptions between groups 2 and 3 and groups 5 and 6, as you saw in the graphs. And these drops occur due to the electron configuration effect. And so first I'm going to explain the drop between group and 3. So first I'm going to explain the drop between groups 2 and 3. And this happens because in group 3 the electron is removed by a p orbital rather than an s orbital like in group 2. And p orbitals have slightly higher energy than s orbitals, so the outermost electron on average is further from the nucleus. And the p orbital also experiences additional shielding from the nucleus provided by the s electrons. And as a result, less energy is required to remove the outermost p electron from the group 3 element compared to removing the outermost electron from the group 2 element. So it's because of the change in orbitals. So now I'm going to talk about the drop between group 5 and 6. And this happens because in group 5, the electron is removed from a slightly occupied orbital. And in group 6, the electron is removed from an orbital containing 2 electrons. And the paired electron in the group 6 element experience greater electron-electron propulsion. And as a result, less energy is needed to remove one of these paired electrons in the group 6 element compared to the unpaired electron in the group 5 element, because the unpaired electron is not being repulsed. So now I'm going to talk about successive ionization energies. And so electrons can be sequentially removed until only the nucleus remains. And the energy to remove each successive electron is called the successive ionization energies. So for example, the second ionization energy is the energy needed to remove one electron from each ion in 1 mole of gaseous 1+ ions to form 1 mole of gaseous 2+ ions. And successive ionization energies provide energy for electron shell structure. So here you see magnesium, which is a group 2 element, but a period 3 element. So we know it has 3 shells and 2 electrons on the outer shell. So the third shell electrons have the lowest ionization energy, and then we move on to the second shell electrons, and those have increasing ionization energies. And then we move on to the first shell electrons, which have much greater ionization energy. And we see there's a gradual increase as each electron is removed. And that is because as successive electrons are removed from the same shell, the remaining electrons experience greater electrostatic attraction to the increasingly positive nucleus. And this increased nuclear attraction requires more energy to remove the next electron from that shell. And that means that the nucleus is less spread out, there's less negative and more positive. And so therefore it can pull in those electrons more and is harder to break that electrostatic attraction. And for magnesium, the second ionization energy is slightly higher than the first, as these electrons are both being removed from the 3s subshell. But there's large jumps between successive ionization energy between the shells, and that is because when reaching a new inner electron shell, there is a big increase in the ionization energy needed to remove the first electron in that new shell, and this happens because the attraction to the nucleus is much greater for inner shell electrons closer to the nucleus. So for example, in magnesium, there was a large jump between the second ionization energy to the third, as the 3s subshell is now full, and this requires the next electron to remove from the inner 2p subshell. And that's all you need to know about periodicity. So thank you, have a nice day, bye!